In 1940, there was this brilliant British mathematician named G.H. Hardy, and he wrote an essay where he basically bragged about how entirely wonderfully useless his life's work was.
Yeah, it's such a great historical anecdote because he studied pure numbers and he was immensely proud of the fact that his abstract theories had absolutely zero practical application in the real world.
Right. But then fast forward to today, and those exact useless mathematical concepts he played around with are literally the bedrock of modern cryptography.
Exactly. They are the underlying mechanics securing your bank account, your text messages, and, your email right this very second.
Welcome to this deep dive. Now, for a lot of you listening, I know just hearing the word mathematics immediately triggers like a visceral full body stress response.
Oh, for sure. It brings back those memories of sitting in high school algebra, just staring at a chalkboard full of fractions.
Right, desperately trying to solve for X so you can pass a test and get out of there.
Hmm.
But today, I want you to take that memory, crumple it up, and just throw it out the window.
We are definitely not solving for X today.
No, we are not. Instead, we are looking at a stack of incredibly fascinating satis. We've got a TED-Ed piece, a mesmerizing TED Talk by Roger Antonsen, and a comprehensive historical text on mathematical theory.
And we're using those to ask one of the most mind-bending ancient questions in human history.
Exactly. The question is, did we invent math to make sense of the chaos? Or is it the secret divine source code of the universe that we are just slowly discovering?
It is the ultimate philosophical koan, really, and our mission today is to help you unpack that debate.
Yeah, we want to show you how looking at the world through this lens isn't about crunching numbers at all.
Not at all. It is a practice that can radically expand your empathy, your imagination, and how you fundamentally understand the world around you.
Okay, let's unpack this, because before we can talk about how math is used, we really have to look at where it comes from. Let's start with the discovered camp.
Which is a perspective that goes all the way back to ancient Greece.
Right, you had thinkers like Pythagoras, who literally believed numbers were living entities. Like, he called the number one the monad, seeing it as the generator of all other numbers and the source of all creation.
Yeah, and then Euclid, the father of geometry, built heavily on that mindset. He essentially believed that nature itself was just the physical manifestation of mathematical laws.
So to that camp, math is a concrete physical reality,
Yeah.
right? Completely independent of human beings.
Exactly. The idea is that if a meteor wiped out humanity tomorrow, a triangle would still have three sides.
Right. The ratio of a circle's circumference to its diameter would still be pi.
Yeah, we didn't create those truths. We just stumbled upon them, like an explorer finding a new continent.
But if we jump forward to the 19th century, the vibe completely shifts. You get this group of mathematicians known as the formalists, and they looked at math not as a divine code, but purely as a human construct.
Yes, there's this massive famous claim from Leopold Kronecker, a German professor, who said, God created the natural numbers, all else is the work of man.
Which is such a bold statement.
It really is. And David Hilbert was another major figure pushing that idea. He wanted to establish mathematics as a pure, airtight, logical construct.
So, to the formalists, math is basically a deeply philosophical game.
Right, think of it like chess. The rules of chess don't exist in nature. Humans just made them up. We decided a knight moves in an L shape.
And once you invent those rules, a nearly infinite number of complex, beautiful strategies emerge from them.
Exactly. But at its core, it's a closed system generated entirely by human logic.
But wait, if it's just a game with made-up rules, couldn't someone just come along and change them? Like, I don't know, deciding a pawn can suddenly move backward.
That is exactly what happened, and it completely shattered the old way of thinking.
Oh, wow, really?
Yeah. For thousands of years, everyone accepted Euclid's flat surface geometry as universal truth. Parallel lines never meet. The angles of a triangle always add up to 180 degrees.
Right, that's just basic geometry.
But then mathematicians like Henri Poincaré started changing the rules of the game. They asked, well, what if we do geometry on a curved surface instead of a flat piece of paper?
Oh, right, because if you take a globe and you draw a line from the North Pole straight down to the equator,
Yep, followed that along.
and then you go a quarter way around the equator and draw a line straight back up to the North Pole, you've just drawn a triangle with three 90-degree angles.
Which adds up to 270 degrees.
That's wild. The old Euclidean rule just completely breaks.
It does. And Poincaré used that exact logic to argue that Euclidean geometry wasn't a universal truth at all. It was just one specific outcome that happens when you use one particular set of rules.
I see. So if you change the underlying rules, you get a completely different, mathematically sound reality?
Exactly. Therefore, they argued, math isn't an independent physical reality. It's just an invented language of abstract relationships.
I have to push back on this game theory, though, because, I mean, if math is just an arbitrary game we invented, why do the rules perfectly map onto the physical universe?
That is the million-dollar question.
Right. If we just made it up in our heads, why does it work so incredibly well at describing the real world?
What's fascinating here is that you've just hit on one of the greatest mysteries in modern science. In 1960, the Nobel physics laureate Eugene Wigner coined a phrase for this exact problem.
Oh, the unreasonable effectiveness of mathematics, right?
That's the one. He pointed out that mathematicians will often invent pure, abstract theories in a total vacuum, literally just playing with numbers for the fun of it.
With absolutely zero intention of describing the physical world, like Hardy from our intro.
Exactly. And then, completely by accident, those abstract theories turn out to be exactly what scientists need decades or centuries later.
The knot theory example in our sources absolutely blew my mind on this point.
Oh, it's such a good example.
Because back in 1771, mathematicians invented knot theory. It was essentially just a complex spatial puzzle, studying how closed loops can be twisted and tangled in three-dimensional space.
Right, it had absolutely no practical use.
None. But over 200 years later, biologists are staring through microscopes, trying to figure out how DNA unravels itself during replication.
Because DNA strands are incredibly long and they get massively tangled up inside the cell nucleus.
Yeah, and for a cell to divide, it has to copy that DNA, which means untangling that massive mess.
Exactly. And enzymes literally have to act like tiny microscopic scissors. They cut one strand of DNA, pass another strand through the gap, and reconnect it to relieve the tension.
And biologists had absolutely no idea how to model this physical process. But it turns out that useless spatial puzzle from 1771 knot theory is the exact mathematical blueprint for how those enzymes work.
It perfectly explains the physical mechanics of human genes. It's almost spooky.
It really is. And we see the same thing with Bernhard Riemann, right?
Yes. In the 1850s, Riemann developed a non-Euclidean curved geometry, purely as a theoretical exercise.
And then fast forward a century, and Albert Einstein is struggling to build a mathematical model for general relativity.
Right, because Einstein knows gravity isn't just a magnetic pull. He theorizes that massive objects actually bend the fabric of space and time.
But Euclidean math only works on flat planes, so he was completely stuck.
Until he realizes Riemann's curved surface math, which had just been sitting on a shelf for decades, is the exact framework needed to prove relativity.
And that's Wigner's whole point, right? That this effectiveness is unreasonable. It shouldn't happen.
Exactly. The universe shouldn't naturally conform to a theoretical game humans just invented on a chalkboard.
So if mathematics is so unreasonably effective at capturing reality, how do humans actually interface with it?
Well, think of it this way. If math is discovered, then the universe is like an orchestra playing a song.
Oh, I like that analogy. So humans didn't write the song, but we did have to invent the sheet music to write it down.
Exactly. According to Roger Antonson's TED Talk in our sources, we do this through the art of finding patterns and naming them.
So he argues that the essence of mathematics is not arithmetic at all.
No, it is simply the act of finding a connection, a structure, or some regularity in the chaos, and then representing that pattern with an invented language.
I love how Antonson broadens the definition here. Because if math is just finding patterns and creating a language for them, then math is everywhere.
It really is. It's far more than just numbers. It is the language of structure.
Yeah, our sources point out that there's literally a specific mathematical language just for tying a tie knot, like left out, right in, center out, and tie. That's an algorithm.
And there's an entire university-level textbook dedicated to the topological patterns of tying shoelaces.
A whole textbook. That's amazing.
Yeah, Antonson even points to tap dancing. A choreographer can invent a notation system to represent the complex rhythms and physical movements of a dancer's feet.
So we observe the physical world, we notice a structure, and we make up a language to analyze it.
Precisely. Like in 1675, Leibniz watched objects fall and invented the notation of calculus to capture the invisible pattern of gravity.
That concept of visualizing the invisible is just incredible. Antonson gives this beautiful visual example in his talk.
Oh, the straight lines one.
Yes. If you take a blank grid and you just draw straight lines, moving one unit down on the y-axis and one unit across on the x-axis, and you just connect them over and over.
Right. You are only drawing rigid straight lines.
But if you step back and look at the whole grid, those intersecting straight lines, mysteriously generate a perfect sweeping curve, a parabola.
You are feeding the system rigid rules, and it outputs this elegant complexity.
It's basically magic.
But once we invent these languages and draw these patterns, the real power unlocks when we shift how we look at them.
Here's where it gets really interesting, because the sources take this idea of shifting perspective and apply it to something as simple as an equation.
Yes, the equation x plus x equals 2 times x.
Right. And when I first read this part of the source material, I was genuinely confused. Like,
Okay.
Antonsen calls this simple equation a metaphor, an analogy.
Which sounds a bit strange at first.
Yeah. I'm thinking an equation is a hard, strict mathematical statement of fact. 5 plus 5 is 10. How can that possibly be a metaphor? That sounds like poetry, not math.
It does sound like poetry until you look really closely at the function of the equal sign.
Okay, break that down for me.
That equality sign is essentially a bridge connecting two completely different conceptual worlds. On the left side of the equation, x plus x, you are existing in the world of addition.
Right, it's a sum. You are taking two separate entities and physically bringing them together.
Exactly. But on the right side, 2 times x, you are in the world of multiplication. It's a scaling factor.
Oh, I see. So the equation is literally saying this specific point of view over here is completely equal to that different point of view over there. It's translating reality.
You nailed it. Every single equation using an equality sign is expressing that two different perspectives lead to the exact same underlying truth.
That is so cool. And Tanitsen takes this concept and goes on this mesmerizing exploration of the number 4/3, just the fraction, 4/3.
Yeah, he takes this single fraction and just ruthlessly shifts his perspective to show how the reality of the number completely changes depending on the lens you use.
Let's walk through that, because it's such a brilliant exercise for the listener to picture.
Absolutely. So numerically, in our standard base 10 system, 4/3 is 1.333 repeating infinitely.
But if you switch your language to the binary system, using only zeros and ones, it looks like 1.010101.
Right, it's the exact same fundamental truth, but an entirely different representation.
Then he looks at it visually as a physical ratio. If you have a rectangle that is 4 units across and 3 units up, that 4x3 box is the exact aspect ratio of an older television or a standard computer screen.
Like an 800 by 600 pixel monitor.
Yeah, and if you draw a diagonal line from the bottom corner to the top corner of that screen, the length of that line is exactly 5. 4, 3, 5.
It's a perfect geometric pattern just hiding right inside the screen you stare at every day.
But the shift to motion is where it gets truly wild.
Oh, the dancing dot. Imagine two circles rotating. The first circle rotates exactly 4/3 as fast as the second one.
So when the fast one completes 4 full revolutions, the slow one completes exactly 3.
Exactly. And if you draw lines from those circles to where they intersect, the dot where they meet dances around in this intricate, symmetrical loop.
And the image of that dancing dot actually is the number 4/3, just translated into motion.
And what does 4/3 sound like?
Right, the audio interval.
Yeah, if you take a pure musical note, just a sound wave vibrating at a specific frequency, and you multiply that frequency by 4/3, you get a new note.
And if you play them together, it forms an audio interval called a perfect fourth. Like an A multiplied by 4/3 becomes a D.
That harmonious chord is the literal sound of the math.
Then you can even shift from pitch to rhythm, and 4/3 is the sound of 3 beats played in the exact same span of time as 4 beats.
It's a polyrhythm, basically a drummer playing a triplet on a snare drum against straight 16th notes on a hi-hat.
And then in physical space, the volume of a sphere is exactly 4/3 the volume of a specific cylinder that encloses it.
From a repeating decimal to a computer monitor to a dancing dot to a musical chord to the physical volume of a ball.
It's astonishing.
If we connect this to the bigger picture, Antonsen demonstrates this physically by folding shapes. He takes a two-dimensional pattern, 4 flat triangles arranged on a plane.
And he folds them up into a 3-dimensional square pyramid.
Right. Then he takes 2 of those pyramids and joins their bases together, creating an octahedron, an 8-sided solid.
And once it's an octahedron, you can hold in your hand to just rotate it on its axis.
And every time you spin it, it looks different. The light hits a new face, it casts a new shadow, the geometric relationships shift.
But it is the exact same object. By simply changing your axis, you prove that changing your perspective reveals entirely new truths about the exact same object.
Which brings us to a really profound point. This ability to fold, to rotate, to change the axis of your perspective, it isn't just a neat geometry trick to show off at parties.
No, it is the fundamental definition of what it means to truly understand anything in life.
Exactly. Antonsen brings in this great ocean metaphor to capture this. If you want to understand the ocean, you can start by looking at a map. You see its geographical boundaries.
And that's a valid perspective, right?
It is. But then you change your perspective and walk down to the shore. Now you can hear the crashing waves, you can smell the salt air.
You're gathering more data, sure, but you are still an observer on the outside.
Right. To get the deepest perspective, you actually have to dive into the water. You have to view the ocean from the inside.
And in mathematics and computer science, looking at a structure from the inside requires a really profound leap of imagination.
You have to visualize a system as if you were standing within its rules.
For me, this is where the deep dive explicitly connects to everyday life. Because stepping out of your own vantage point and looking from the inside of another structure out, that is the exact definition of empathy.
It really is.
If you can change your perspective mathematically, if you can see a fraction as a rhythm and an equation as a metaphor, you're practicing the cognitive empathy required to view the world from someone else's shoes. Empathy is just applied mathematical imagination.
The sciences of math and computing demand that you constantly step outside your own assumptions and inhabit a different set of rules.
But as incredible and universal as this tool of mathematics seems to be, our sources bring in a massive historical reality check.
Oh yeah, it has hard boundaries.
Right, because we spent the first part of this deep dive talking about how mathematicians like David Hilbert wanted to prove that math was a perfect, complete, airtight logical game.
He thought we could eventually prove every single truth in the universe using mathematical rules.
But in the 1930s, a logician named Kurt Gödel completely shattered that dream with his incompleteness theorems.
Gödel's work is incredibly dense, but the core mechanism of it is brilliant. To understand how he broke mathematics, you have to think about the classic liar's paradox.
Okay, remind me how that goes.
Imagine someone says the sentence, "This statement is false."
Oh, right, because if the statement is true, then it must be false. But if it's false, then it must be true. It's an endless loop.
Logic completely breaks down.
Yeah.
What Gödel did was figure out a way to translate that exact linguistic paradox into rigorous mathematical notation.
He created a mathematical equation that essentially said, this equation cannot be proven.
Yes. And by doing that, he mathematically proved that within any complex logical system, there will always be true statements that can never be proven using the rules of that system.
That is heavy. He literally used math to prove that math has limits.
He did. No matter how much math you invent, it will always be fundamentally incomplete. There are true facts about the universe that are simply beyond the reach of logical proof.
And Alan Turing followed that up in computer science, right? By proving there are specific problems that are uncomputable.
Exactly. No matter how powerful your AI is, no matter how much time a supercomputer has, the machine will never be able to solve them. Even this infinite universal language has walls it cannot climb.
So what does this all mean? If we zoom out and look at everything we've talked about today, math is not about agonizing over fractions or memorizing times tables. It's a tool.
A tool to cultivate a mind like water.
Yes. Whether you believe mathematics is a divine code we are discovering or an incredibly useful logical game we invented, studying it trains your brain to be flexible.
It teaches you to spot hidden patterns in the chaos.
And most importantly, it forces you to practice the imaginative empathy of taking a single truth and daring to look at it from a dozen different angles.
This raises an important question, though, because we've seen how Wigner's unreasonable effectiveness shows math brilliantly describing physical reality.
Right.
But we've also seen Gödel's proof that math is fundamentally incomplete.
So the final thought we want to leave you with, something to mull over on your own. If Gödel proved that mathematics contains fundamental truths that can never be logically proven,
And math is the language we use to describe reality.
does that mean the universe itself is fundamentally incomplete?
Or does it mean that human intuition, our strange, unquantifiable ability to feel a truth without a logical proof, is actually a higher form of understanding than the universe's ultimate code?
It really makes you wonder what perspective we need to shift to next. Keep finding those patterns.